We do a fair amount of work with Linux, in particular a lot of the real-time extensions to Linux. Our robotics arms that we're working on for NASA all use the real-time extensions. We also have quite a bit of flight software that we've created. We were the folks that put the first Linux in space in orbit. That was on a TACSAT, Navy TACSAT, and it was a real flyer because they weren't quite sure whether Linux would actually work in space. It's like, it's software, why wouldn't it work in space? But the problem with the satellite business is that it's an old boy network, and you can do anything as long as it's VxWorks. If you try to do anything that's not VxWorks and not a RAD 750 processor, then they're nervous. So in any case, we've had a lot of success in that area. I've been using Linux myself since about 2000. I've been running native Linux for a long time. I hate to start Windows if I can avoid it. Unfortunately, when I'm teaching a WebEx session, I have no choice. I have to kind of get on there and use Windows. My background, about 39 years in the industry now. I've been developing on RTOSs, bare metal equipment, as well as Linux for quite some time. So let's kind of move on here. What we're going to talk about, this is all about ARM debugging. Now, when I say ARM, I mean both Cortex-A, Cortex-R, and Cortex-M platforms. So some of the things that we'll be talking about are specific to the Cortex-M. Some of them are specific to the Cortex-A. We'll kind of outline those as we go through. We'll talk about JTAG. We'll talk about single wire, or actually it should be serial wire debug and serial wire output. I was typing a little too fast there. OpenOCD, CMSIS-DAP. There are so many options for doing debug on the ARM, and it really depends on how the manufacturer decides to implement it. So we'll see lots of options here, and we'll also kind of do a little bit of work with OpenOCD so that you understand how that works in conjunction with JTAGs. So understanding the debugging spectrum here, ARM-based processors have been changing consistently over the last several years. They continue to add new capabilities. ARM just introduced the Cortex, the V8M architecture, which of course is a standard V8 architecture, but is for microcontrollers. And what they did in that, they also introduced the concept of trust zone into the microcontrollers. Trust zone has been inside of the A processors for quite some time, but they have everything that ranges from really small Cortex-M0 microprocessors all the way up to the Cortex-A72s. So these are big 64-bit platforms, and of course this is ARM's move against Intel to try and take some space in the data center from them. Debugging for this can range anywhere from real simple printk, printf, printk type operations all the way up to hardware interfaces and using hardware for debugging. We'll talk about both of those here. So when we start getting ready to do debugging on the core, small processors themselves may be running some lightweight RTOS, or often cases they're running bare metal. When you're running bare metal, you don't have a whole lot of options in terms of what you can debug. There are very specific steps that you have to go through in order to debug those kinds of platforms. You know, we're talking less than 512K worth of RAM, less than a megabyte of flash. For a typical Cortex-M0 Plus, you're looking at 32K bytes worth of RAM. So in terms of being able to put a lot of software debug in place, there's not a whole lot of room to play with there. So there are a lot of different techniques that can be used on these small processors. Of course, printf style statements are one approach. Blinky LEDs, and never underestimate the power of a blinking LED. It does several things. First of all, it lets you know that something is actually happening. More importantly, it is incredibly entertaining to management. When they come by your cube and ask you what you've been doing, you go, "Here, let me show you this," and it blinks and they go, "Wow, that's cool." Especially if it's a blue LED, that's even more interesting. They found that people are willing to pay up to 10% more for products if it's got blue LEDs instead of green LEDs. So it's always important, if you're doing a custom board, make sure you put some blue LEDs on it, because people go, "Ooh, that's cool." And but beyond the blinky LEDs, there are a lot of hardware debugging interfaces that are available. We talk about JTAG. We'll certainly get into all of these in this next few charts. core site, which is the basic macro cell mechanisms that ARM includes. And then there's some variants there of serial wire debug, serial wire output, OpenOCD, CMSIS-DAP. There are a number of different interfaces, and all of them work slightly differently, unfortunately. So the first two, obviously, printfs and blinky LEDs, are essentially free. The rest of those can actually cost you quite a bit of money. Depending on what sort of feature set you're looking for, you can get a very basic JTAG interface for about $70. Even less if you're willing to use bus pirates or something that is not really meant to be a JTAG, but you can trick it into being a JTAG. And then that can be as much as $10,000 on the ARM. I've actually seen Lauterbach units that are quite a bit more expensive than that. Generally, what you're going to see here is you're going to get what you pay for. You're not going to get a whole lot of support and services for $70. But if you're willing to spend a little bit more money than that, you can get trace buffers, you can get a whole bunch of other capabilities in there that are really valuable if you understand how to employ them. So those are for the micros. On the mainstream side, especially when we're dealing with Linux, we see the debugging piece is really broken into two different phases. We have kernel debugging and we have user space debugging. In the kernel debugging, we have two pieces in there as well. We have early debug of the BSP, or statically linked device drivers. This is going to be really early in the boot cycle. You're not going to have access to a lot of resources at that point in time. The second piece is debugging of loadable kernel modules. Now, loadable kernel modules, once we get to the point where we can do a loadable kernel module, then we actually have quite a bit of services that are available to us over and above what we would expect to see in an early debug cycle. For user space debugging, this is normally where we see GDB. And GDB is pretty much the de facto standard for user space debugging inside of the kernel, inside of Linux user space. It is possible to reach out and touch hardware from user space. They have a couple of different ways of doing that. There is, in fact, a user I/O module, a user I/O section that allows you to then reach out and touch physical hardware from user space. Obviously, you have to have the right sorts of permissions to be able to do that. You can, in fact, access all of the physical address space from user space if you can get access to /dev/mem. There are some versions of the kernel that also have /dev/kmem, and that device maps just the kernel's address space. So it is very possible to be able to reach out to physical hardware and then make it do things like blink LEDs or toggle GPIOs. Hardware debugging versus JTAG in user space. It is possible, but it's very rare in user space because you have to have what's referred to as a run mode debugger. And most of the JTAGs are stop mode debuggers. So there's only a few of them that support run mode, actually only two of them that I know of. One from what used to be American Arium and the other one from Lauterbach. But both of those start at like $7,000 for one of those debuggers. Believe me, if you're at the point where you need a JTAG in user space, yeah, you're probably in way over your head. If you can't debug it with printfs and GDB, then I sound a little like Linus. If you can't debug with printk, you shouldn't be in the kernel in the first place. Yeah, if you feel you need a JTAG in user space, then perhaps you need to get some additional assistance somewhere along the line. With early kernel debug is really tricky. It's tough to do because early in the boot cycle, you don't have most of the hardware available to you. You're actually going through the initialization, you're setting up SMP, you're setting up the memory management unit, you're handling the transition from physical address space to virtual address space. So all of the addresses then change. There are a lot of unfortunate circumstances in early debug that make it very, very difficult. If you have a statically linked device driver that has a kernel panic in it, then you're in deep trouble because it's very difficult. You can't capture the output. There's no place to write it to, and it just simply crashes on you. That is not an impossible situation to debug. It's just complicated. Of course, kernel oopses are more common in these statically linked device drivers. So by statically linked, I mean you're going to link it at compile time of the kernel. So it's going to be there in the kernel forever. You're not going to be able to get rid of it. Now, there are some mechanisms, however, that allow us to debug in that particular environment. One of them is to turn on config early printk. It's an option in the kernel. When we turn this on, it's going to allow you to dump the print K output to a frame buffer or to a serial port. And you can also put you can put timestamps on it. So you can actually look at the timestamp and say, okay, what is it doing? Okay, no, okay, there's the time, there's an overlap in time or something like that where we're getting a race condition that's causing us to crash. So that's definitely an option for us. And a lot of the kernel developers, as a matter of fact, I think a couple of years ago when we kind of did the survey of kernel developers in the room, we said, how many people are using config early print K as their debug mechanism? And it turned out 75% of us were using that as our primary debug mechanism. On the other hand, if we have access to a JTAG or serial wire debug interface, then that makes life so much easier. We'll talk more about that when we get into the actual interfaces for that. Now, Linux kernel module, loadable kernel modules. LKMs, there are a couple of options that are available to us. One is KDB. Now, KDB is a symbolic disassembler. It's not really a debugger in the standard sense that we would think of a source code debugger. So with KDB, if you're familiar at all with real-time operating systems like VxWorks, KDB is like the VxWorks shell. You have the ability to set breakpoints, single step. It's all in assembly language, however. So if you don't speak the assembly language for your processor, then KDB is probably not going to do you a whole lot of good. However, I have used KDB in many cases. For instance, I was debugging Android on a cell phone, and I had KDB turned on, and when I got a kernel oops, it would dump out to the KDB prompt, and then I'd be able to sit there and ask it what it was doing, dump the variables, dump the stack, show me what was running, what kernel modules were loaded. So there's a whole bunch of stuff that you can do with just a simple interface like KDB. KDB used to be a significant patch to the kernel. It's now part of mainline. KDB is now just a front end for KGDB. Now, KGDB operates via the system's console port. There used to be all kinds of interesting variants of KGDB. We had KGDB over USB, KGDB over Ethernet, KGDB over this, that, and the other thing. Unfortunately, that required the KGDB code, the actual debugger code, to reach out and touch a little over 300 different files. And Linus was in the position of not only no, but hell no, you're not getting anywhere close to that number of files just to add a debugger. And that was one of the reasons why he was so adamant against debuggers for a long time. Fortunately, in 2.6.26, they managed to trim KGDB down so that it touched a minimum number of files and then would operate over the console port. Now, the tricky thing for an x86 is where is the console port? And that depends on how you've got your kernel configured. In many cases, it's just the keyboard, mouse, and monitor interface. And that can be tough if you wanted to see something that just scrolled off the screen. Unless you have the scroll back buffer turned on for the frame buffer, you're not going to be able to do that. So it makes it somewhat complicated to debug. On the other hand, we can also redirect the console out to the serial port. So if our device happens to have a serial port, then we can capture the output on a serial terminal like Minicom and then be able to scroll back and take a look at exactly what was happening when it failed. Again, with Linux kernel or loadable kernel modules, you can use a JTAG or single wire or serial wire debug if they're available. I'll show you an example of that a little bit later here. Another important tool is, and this is one of the ones that software people often will overlook, and that's the use of hardware like oscilloscopes and logic analyzers. It's really kind of fun to walk into your hardware guy and say, can I borrow the oscilloscope? And he looks at you as a software guy and goes, you know what an oscilloscope is? And it's always kind of interesting. But what we can do inside of our code is we can toggle a GPIO pin. If we have some way of reaching out and either lighting an LED or toggling a GPIO pin, we can then capture that inside of the logic analyzer. The output that we see here, this is actually from my SAILI logic analyzer. The SAILI S-A-L-E-A-I. It's a really strange word. But the SAILI logic analyzer is about $500 for an 8-channel logic analyzer that runs off of USB 3, but it'll give you 200 megasamples per second. So it's a very fast logic analyzer. And one of the advantages that it has is it has built-in decoders for SPI-bus, I2C, and several other protocols. So especially if you're trying to access SPI flash, or you're trying to access something else that's hanging off the I2C, you can actually watch it, and it'll interpret the bits so that you can actually try to figure out what went wrong. Of course, other inexpensive PC-based oscilloscopes, they can be fast enough. I mean, you really only need about 50 megasamples per second, and that'll capture most things that we're dealing with in the kernel. But again, you have to be able to get access to a GPIO pin someplace. That's usually not a major problem for most of the ARM SoCs. They usually have a plethora of GPIO pins. So it's really just a question of finding which one you want in the middle of the, our friend, the device tree structure. That can be easier said than done. But there's also a project called the SIGROC project. That particular project has done some great work at being able to use logic analyzers and things like bus pirates and other inexpensive interfaces for being able to do some pretty significant debugging inside of the kernel. So if you're interested in what they've been doing, go out to sigroc.org. They'll kind of walk through some of the interfaces that they already have working, and they'll show you some examples of what you can do with those kinds of devices in order to help debug in the kernel. Of course, kind of the daddy of all of the debugging interfaces is the JTAG port. Now, the JTAG port is IEEE 1149.1. There's now an 1149.2, which increases the speed of the JTAG. The JTAG was originally designed as a replacement for the bed of nails. So we see a bed of nails right here, and this is the kind of thing we would expect to see for one of these types of devices. You would open up the lid, you would insert the board, you'd close the lid, and there's little test points that come down, and it powers the board, and if you read the right voltages in the right places on the board, you say, it's good, and you would ship it. Bed of nails, they're still in use. We still see them used occasionally, but the reality is that the bed of nails, especially with today's boards, you're talking about 462 ball BGA, micro BGA interfaces. There's just too many things to try and instrument in order to be successful with one of these bed of nails approaches. So what they did was they implemented the Joint Test Action Group, which is where JTAG comes from. It's actually entitled the Standard Test Access Port and Boundary Scan Architecture. But that doesn't roll off the tongue quite as well as JTAG does, so everybody just calls it JTAG. This was originally introduced in the 1990s, and the advantage that you had of it is that because it is a boundary scan protocol, it means that it looks at all the pins, and you can then select which pins you wanted to look at. Typical data rate here, we're talking 100 kilohertz kind of data rates off of it, but that turns out to be more than fast enough for most of the events that we would be interested in. The JTAG scan chain also incorporates not just the processor. It can incorporate Ethernet chips, it can incorporate multiple cores, you can have multiple processors. So when we talk about the JTAG scan chain, we're really talking about a potential for being able to see virtually all of the major interfaces on a particular board. So JTAG, though, is a really simple serial protocol. There's really not a whole lot to it. They have these devices that they call wiggler-style interfaces that just wiggle the wires. And what these things do is they clock data in and out. Typically what they have here is they have their test mode select. We can then determine which device we're going to select by using the test mode select option. And then we would have test data in, test data out, and then the clock. These would then give us the ability to then talk to any one of the devices at any point in time and then read all of its information out using one of these serial interfaces. So this is a fairly standard sort of connection these days. We have a maximum speed. They started out at 100 kilohertz. Now it goes up to 100 megahertz with the 1149.2. A ribbon cable is typically more than enough for being able to connect to one of these things. And the connection to the development host, depending on whose manufacturer you happen to be using, I've seen parallel ports. USB is probably the most common these days. I've also seen serial port versions of JTAGs and Ethernet versions of JTAGs. Of course, USB tends to be one of the cheapest of the interfaces. You don't find PCs with parallel ports on them anymore, so finding a parallel port JTAG, although I have one of them, it's more for historical purposes. You know, it's inside of a glass case. It says, in case of emergency, you know, break here. But fortunately, I don't have to break out that one very often. With USB, we have a fairly inexpensive interface, and again, these can range in price. It turns out that one of the companies, this one here, the Sager guys, they actually have an education JTAG that they will sell for $45. And it has a USB interface on it. So it is fully functional in the sense of what it does. It's just not as fast as their high-end units that have Ethernet on them. The high-end units with Ethernet and USB will cost about $1,000. So there's a much more expensive interface. However, the nice thing about having Ethernet on it is I can be anywhere in the world. As long as I have network connectivity, I can reach out and start debugging. So I don't have to be co-located with the board. Obviously, it's better if I am co-located with the board, but especially if I'm trying to debug something that's rack mount, there's a lot of noise inside of those computer racks, so I hate to be sitting next to them if I can avoid it. We see, again, a lot of these, so we see here's the McGregor Wiggler style, we have the Sager J-Link interfaces, and the J-Link interfaces represent kind of a standard in the Cortex-M series parts. You'll see a lot of the interfaces that are coming off of machines like the ST32, or STM32 rather, from STMicro. They have an STV link, which looks just like the J-Link interface. So J-Link has kind of become as close to a standard as you can expect to find, especially in the microcontroller versions of the ARM. The bigger ones, you have the BDI 2000, now that's out of date. We have the BDI 3000. These, again, Ethernet versions that then attach directly to the device. We'll see a little bit more about that as we go through. Now, the JTAG user interface, and this is where I have to admit a bit of a personal bias. I prefer JTAG interfaces that have a GDB-style interface on them. That is, I can use any version of GDB, any front end that speaks GDB, I can then talk to the JTAG. I hate to have to start up another manufacturer's user interface just to be able to talk to the JTAG. And what grinds me even more is when I have to run Windows to do that. Using Windows to debug Linux, there's just something wrong with that. I'm sorry, I just can't do it. So I really tend to focus on JTAGs that have a GDB interface on them because that gives me the most flexibility. I can then, if I have to, I can talk to it from the command line using my Android phone as a dumb terminal. Those are the kinds of things. Sometimes you get into that kind of mode, hopefully not often, but it does have the ability to give me a lot of options in that case. There are a lot of others, a lot of these JTAGs that have Eclipse interfaces in them, Eclipse plugins. So if you happen to be of the Eclipse mindset, then you have a plugin that you can plug right into the environment. You can have then the developer, you can have the compiler, the editor, the debugger, everything in one nice, neat little package. For those who like GUIs, then it certainly is a viable option. There are very few JTAGs, however, that work in OS X. So if you're interested in doing a lot of work where you might require a JTAG, you'll really have Windows and Linux are your two primary choices. It turns out the Sager does in fact support OS X, so it's one of the few that do. But, and I think OpenOCD also sits on top of OS X as well. So we'll run into OpenOCD a little bit later in this presentation. So what exactly can you do with a JTAG? Well, a typical JTAG has the ability to reflash. So we can go out, reburn boot. So if you have boot firmware, we can use the JTAG to flash the boot firmware. We can use the JTAG to debug the boot firmware itself. So this is another one of those environments where it's very difficult to typically debug inside of something like U-boot simply because it's at such a low level. It's dealing at the physical addresses of the part, and you're at the assembly language level for a good portion of the initial boot cycle inside of U-boot. So when you're turning off when you're setting up the chip selects, you're turning off the data cache, invalidating the instruction cache, disabling the MMU, turning off the interrupt controllers, setting up a C calling stack. All that stuff is done in assembly language. So with a JTAG, we can debug that. Without a JTAG, yeah, you're really kind of on your own on that one. It's going to be really difficult. So we can use the JTAG as a general debugging aid. It turns out that because the JTAG was built as a test tool, it's really out there for being able to do things like do walking patterns, barber pole patterns, and things like that in RAM. Some JTAGs are actually scriptable. So you can set up a pattern, you can set up a test that will then test every single bit in memory continuously. Maybe you're going to do that over the weekend just to make sure that everything is working correctly. You don't have a stuck bit or something like that. So JTAG was originally out there as a mechanism for the hardware people to debug the hardware. But it turns out because of the way the boundary scan protocol operates, we can actually use that to debug software as well. So we can go out and strobe a location in memory. We can talk to the I²C. We can do all kinds of things from within the JTAG interactively, which we would normally have to have written code to try and do. The big problem that's kind of the long pole in the tent with JTAGs are the hardware configuration files. The hardware configuration files have to describe all the registers of the processor core. We also have to, in many cases, describe all of the registers of the peripherals that happen to be loaded on the motherboard. We have to describe whether they are 32-bit, 8-bit, 16-bit, read-write, read-only, write-only registers. There are write-only registers, and those add interesting complications because you write a value and then you don't know what you wrote. There's definite steps you have to take in order to deal with write-only registers. And with these, unfortunately, there's no one common syntax. Every manufacturer has their own different syntax for being able to describe the board. Now, once you understand one syntax, you can look at it and then typically translate it over to another syntax. But it is kind of a nuisance. Now, the advantage, though, of being able to get these configuration files right is in the configuration file, you'll actually specify the address that you're writing to and the value you want to write. So you're literally programming the chip from the very first portion of the boot cycle, the power on jump cycle, just to get it to the point where it will actually access memory. Once you get that right, you can actually translate that into the assembly language that's required for the bootloader. So being able to use the JTAG in this very early boot cycle before Linux even begins to run gives us the ability to then take what the actual register accesses we're doing and translate them into assembly language, because that's what we have to have ultimately to run in the early boot stage. Now, another problem that we're running into with JTAG at this point is that there is no common JTAG connector on most boards. It varies widely from manufacturer to manufacturer. Now, there is a typical standard for ARM, and that's going to be the 20-pin ARM connector that we see here in this JTAG picture. But that 20-pin ARM connector, it's got typical 1/10 of an inch spacing, 0.1 inch spacing. But TI uses a 14-pin variant of this. So it is similar, but not quite the same. So that means that if we want to debug on top of TI silicon, we have to get the 20-pin to 14-pin adapter. Then we have here, with the smaller Cortex processors, they introduced a 10-pin connector. This 10-pin connector, what was felt was that this 20-pin 0.1 inch spacing was too big a connector. It took up too much physical real estate on the board. So they shrunk it down to a 10-pin connector that used 1.5 millimeter spacing. So it's teeny tiny. But that also means it's very easy to bend the pins. So you do have to be somewhat careful when you're dealing with these 10-pin connectors. And then there's a 20-pin variant of that 1.5 millimeter spacing that has JTAG and the embedded trace modules. So we'll talk about ETM here in just a moment. So that is just part of the connectors we could potentially encounter for JTAG. We'll see a couple of others here in just a moment when we start talking about serial wire debug. Now, the ARM core site is ARM's answer for debugging. And it is a series of modules that are incorporated into the actual silicon SoC. However, the manufacturer has to think far enough ahead to actually do that. It is an optional part of the ARM architecture. So we can absolutely have SoCs that are made that don't have any debugging capability whatsoever. Of course, that makes it all that much more complicated to try and bring them up. So most manufacturers will think far enough ahead to say, well, maybe we want to give them the capability of doing some debugging. Inside of that, inside of the CoreSight series of parts, and we'll actually see a picture of that coming up here, we have the ARM debug interface architecture, and then there are a series of real-time trace macro cells that are available. We have the embedded trace macro cell, the program flow trace macro cell, and the system trace macro cell. And again, all of those are kind of optional. You might have one that has program flow macro cell, but not embedded trace macro cell. So there are lots of cases where you'll have to kind of look at the individual manufacturer's SoC description to see what features they have incorporated inside of the SoC. This is all part of the CoreSight component architecture, and it supports a very high-speed serial trace port. So here's what the CoreSight architecture looks like. We have the ARM access bus here, and then we have the system trace module. So this is a system trace macro cell. This is going to go off to the trace bus, and then we have embedded trace macro cells. We also have serial wire debug sitting out here, and DAP. We'll talk about that here in a moment. So these are all mechanisms that we may have available to us on our SoC if the manufacturer actually made them visible or incorporated them at all. In general, we will have our access over here through the debug tools. So this is going to go through the debugger interface unit, and we should be able to then watch what's happening on the bus, assuming that our CoreSight chip and debug trace IP is working the way it's supposed to. But again, this is IP. The manufacturer may or may not incorporate this IP onto their SoC. There's a lot of taxonomy that goes along with CoreSight. We have the advanced microcontroller bus architecture. That's the AMBA interface we were talking about just a moment ago. There's a lot of advanced trace bus things, debug access ports, several trigger architectures. We won't go into the details on all of these. Embedded trace buffers. Now, embedded trace buffers, this is the piece that implements the trace macro cell. The trace macro cell is really important in certain cases, especially when we're trying to debug multi-core systems, because the trace macro cell allows me to see not only what instructions are moving on the bus, but also the timing of the bus operations themselves. So especially when I'm trying to debug very tight tolerance race conditions inside of the kernel, it's great to be able to get access to these traces. Of course, we then have serial wire debug and the system trace macro cell. There's a whole bunch of other things. Again, we'll get to all of these as we go through. The ones that we will find more often than not these days in SoCs. The problem with the JTAG is that at a minimum, it will require at least 4 to 6 pins to implement a JTAG. If we look at that 20-pin connector that we just were talking about a moment ago, it turns out the vast majority of those pins are actually ground pins. So they can eliminate a lot of the ground pins, and that's what got it down to a 10-pin connector. They used a 10-pin connector because that was the next most convenient small size. The reality is you can implement a JTAG in either 4 to 6 pins depending on how you go through the implementation. But for a very pin-constrained SoC, that's considered to be not enough pins. They don't have enough pins, rather. They don't have enough pins to implement the 4 to 6 pins for the debug. So what they do is instead they replace it with serial wire debug. With serial wire debug, you only need 2 pins. You need clock and the data pin. And with that, you then can reduce the number of pins used for debug on the SoC, and that means you have more pins for GPIOs and other normal outputs for the SoC. So we have the single wire debug input-output pin and the single wire clock. These are typically overlaid on top of the TMS and T-clock pins. So you'll see something that looks kind of like this. This one happens to be from an STM32 microcontroller board. But we have the 2 pins that are actually the ones of interest. We have our clock and we have the data. And then the rest of them are usually either grounds like this one are, or they're reserved for one reason or another. So serial wire output is very similar to serial wire debug, except that it's basically your ability to do print Ks or printfs out through a 2-wire interface. So it is terribly handy to have access to this, as well as being able to then deal with an integrated trace macro cell. So the integrated trace macro cells If we look at the kind of the overarching piece of that, which is the embedded trace macro cell, what this does is it has the ability to capture state changes on the bus. So as we're looking at this, we're looking at an instruction interface. We can catch the instructions. We can look at a control bus. There's data address interfaces, so we can see what data addresses are actually being strobed on the bus. We have the instruction pipeline interface. We have the data value interface, a coprocessor interface, the infamous CP15 interface for ARM. A lot of these things are then available to us through these trace macros. Now, the problem is that you have a JTAG and then there is a trace module, and they are usually priced separately. The trace modules can have, I've seen some of them that have as much as 16 megabytes worth of trace, but when you're talking about 4 megabytes worth of trace, it's extremely high-speed memory, and it's very expensive. You may be adding thousands of dollars to the cost of the unit by adding the trace mechanism. If you are just simply trying to debug kernel code that isn't really hardcore timing, like you're trying to bring up multiple cores at the same time kind of thing, then the trace module, you probably can do quite nicely without it. But if you're at the level where you're trying to initialize the chip, if you're trying to get it to do anything to light it up, then you may need the trace macro cell just so that you can figure out what the thing's doing at any one point in time. So unfortunately, not all ARM SoCs support the trace macro cell option. So again, you have to look at your manufacturer and find out from his data sheets whether or not they have in fact included this capability. There's another debug interface where they take the serial wire debug output and then they redirect it to something that looks like a USB file system. In this particular mode, and we see this with the Freescale Kinetis parts, these look like disk drives. So when you plug the device into your development host, it presents a disk drive interface that you then simply copy your object module over to the disk drive and it burns the flash on the part. It also is a JTAG interface. So we can see not only the ability to just copy things over and have it automatically program the part, but we also get the ability to do software debug through the same interface. So it's a drag and drop sort of interface to an apparent USB drive. And then of course it also has a USB serial interface for printf style debugging. So we can use a JTAG if we want to use OpenOCD, for instance. In many cases, they'll be able to talk to these interfaces. We also have the ability to just do printfs inside of the code or print Ks inside of the code if we're doing kernel code, and then we'll be able to see it that way. CMSIS-DAP is another interface. This is ARM's Cortex microcontroller software interface standard, and you have access to the debug access port, which is where the whole CMSIS-DAP comes from. This is typically going to be routed via USB interface to a host debugger. So again, it looks like serial wire debug or JTAG interface, but it's just simply presented on top of a USB. So here we'll typically see things like the FTDI, the 2232H, which is an FTDI serial interface. It's a dual channel serial interface. One channel is for the serial output, the other channel is for the debug, for the JTAG input. So that is another very common thing that we'll see. We're also starting to see it happen more often in SoCs that have, say, a Cortex A9 and a series of Cortex M3s or M4s embedded inside of the core. So we may use a standard JTAG to get access to the A9, but we may be able to use CMSIS-DAP or OpenSDA or one of these other techniques for be able to get access to the Cortex M3s and M4s. So it is kind of a cool interface if you do happen to have something that supports it. OpenOCD supports CMSIS-DAP now. So there are several pieces of software that are available that can use it. It is kind of an alternative mechanism to using the embedded trace macro cells. Certainly it takes a lot less silicon in the SoC to implement this than it does to implement the full up embedded trace macro cells. All right, so how do we take advantage of all of this? One of the techniques, of course, is to use the OpenOCD project. The OpenOCD project's been around since 2008. We are now in version 10 of OpenOCD. If you go to the GitHub repository, if you go to the OpenOCD page, it's version 9. So in that case, you're better off to actually go to the GitHub repository and pull down the latest. Now, this will support a lot of the high-end ARM processors, TI DaVinci, Cortex-A9. I think it does A15 now with version 10. It is hosted as a Git repository, so you can go to this website and be able to pull it down that way. It provides a GDB interface. So that means that we can use DDD or any of the standard GDB front ends, including Eclipse. We'll be able to hook up directly to OpenOCD. It does interface nicely with Wiggler-style JTAGs. It turns out that they have like 49 different interfaces or something along those lines of different JTAG interfaces that OpenOCD supports, including the bus pirate, including the SAILI, including a lot of these logic analyzers that can be then twisted to make operate as though they were JTAGs. This is supported on Windows, OS X, and Linux. And the nice thing is there are pre-packaged versions available for most of the development hosts. So you don't have to compile it from source. Personally, I do compile it from source because I like to be on the bleeding edge and see all the interesting bugs that they have in OpenOCD. But nonetheless, it gives me kind of the latest and greatest in terms of the interface that they are supporting. With OpenOCD, basically you run the OpenOCD server and then it presents a socket interface. So when you start up GDB, you tell it to do a target remote and to connect to port 3333. That will then connect you to the OpenOCD server. When you're connected to the OpenOCD server, you can do things like this. You can tell it monitor dump memory word-wise at this location. So you can actually bypass the GDB interface and talk directly to the monitor. That is, if you're talking to, for instance, U-boot or something like that, you can actually talk physically to the monitor as well. Now here we see DDD, which is one of the front ends that I typically will use. We see the GDB command line down here. We see the code being displayed here. We can set breakpoints. We can then single step through code. We can single step source code, or we can single step at the assembly language level. So we have the option of doing both of those. And again, here's an example. We would start up DDD, we'd specify -debugger, and then we have to give it the version of the debugger that we happen to be using. The VM Linux image is the image that was compiled with kernel debugging turned on. In order to actually debug Linux kernel code, we have to compile the kernel with debugging enabled. Now, fortunately, you don't have to run that kernel on your target. You just have to make sure that you've compiled the kernel. That's the kernel you're going to run on the target, and then you compile the kernel again with debugging turned on, and that's the version you're going to give to the debugger. So you don't have to run the debug version of the kernel on the target if you don't want to. The disadvantage of the debug version is it adds about 30% to the size of the image. So this has got a lot of symbol table information in it. You can load that over to the target. It doesn't really matter. The symbol table information will get stripped off because it's really there for the debugger's purposes. But this is one of the reasons why you want to save a copy of your VM Linux. So when you compile the VM Linux for debugging, that's the one you're going to copy off. You're also going to copy off the system.map. So when you build the kernel, you've got system.map, that's your symbol table at compile time, and you have the VM Linux, which incorporates that symbol table into the actual image. So when I start my debugger and I tell it to use that VM Linux image, which is what I did back up here, now I've pulled in all of the symbols that were visible at compile time in the kernel. Once I have that, I can then debug anything that was statically linked into the kernel. Now, unfortunately, loadable kernel modules aren't statically linked into the kernel. So that means that the loadable kernel module symbols will not be visible inside of VM Linux. We have to do something in order to add those symbols. So here's an example of what we would do to turn on kernel debugging. This happens to be in my kernel here for 4.2.8. Inside of this, we'll click on the kernel debugging option, and we'll just simply rebuild the kernel. Now, at this point, anytime I build a loadable kernel module that uses this particular kernel as its basis, will also have debugging turned on. So it will look inside of the .config, see that it's got debugging enabled, and then that makes all of my loadable modules also have debugging turned on. Now, in order to load symbols into the JTAG UI, I need to attach the JTAG to the hardware and reset the board so that the JTAG is now in control. Normally, I'll set a hardware breakpoint using the JTAG. That way I can handle the transition from physical to virtual space when I'm going from the bootloader into the actual Linux kernel itself. I'm going to load VM Linux into the JTAG interface, and then I'm going to tell the JTAG interface to go. At that point, it will start running, and then when it hits that hardware breakpoint, it will stop, and then I can start doing other things with it. When you encounter the hardware breakpoint, you can then step in assembly until after you get the MMU enabled. Once the MMU is enabled, then we're in virtual space at that point, and now all the symbols, the addresses that you saw in the system.map, all apply. The output of the symbols in system.map are virtual addresses, not physical addresses. So we need to be able to deal with the fact that we're looking at virtual and we're running in the very first piece in physical address mode. So it does get a little bit more complicated, but often what happens, and this is a common complaint that we see on Stack Overflow and other places, you have this thing that says uncompressing kernel image, ... okay, and then it just hangs. And everybody's like, what do I do now? It hung. Well, it turns out that there's lots of print K output. You just can't see it because the device driver that would have output the print K hasn't been initialized yet. So what we can do is if we look inside of the system.map, we'll see a symbol called underbar log underbar buff. Now, log buff is the print K output. It's the raw print K output, but at least it's still ASCII text. You can still see things in it. So you'll notice here that this comes up at a C0 address. So this is up at the 3 gigabyte boundary in virtual space. We need to figure out what our translation is from virtual space to physical space. In the case of the x86, at least in the 32-bit x86, it's pretty easy. Just simply strip off the C0 and you've got the physical address. So what we can do at this point is we can use the JTAG in physical address mode and tell it just to dump that location. And we'll see the entire print K buffer. So anything that happened inside of the system, any print Ks we embedded inside of our driver that was being initialized statically is still there, it's still visible. We just have to have the JTAG to get access to it. Yeah, now normally in the early boot cycle, you wouldn't have gotten to the point where you hit the wraparound in the D message output. Yeah. Yep. Yeah, if it does wrap around, then yeah, you have to stop it a little bit earlier in the boot cycle. Now, to debug a loadable module, one of the issues that we have to understand, if we're debugging the early initialization code, the very init_module entry point of the module, if we have to debug that, then what we have to do is we have to set a breakpoint in the module, in the actual, it's called load module function. It's inside of module.c. In the 428 kernel, that's around line 3233, you'll see a piece of code that looks like this. This do one init call. If you set a breakpoint on that, you're going to stop the system before it runs the init module code. So this is very early in your boot cycle, very early in your module initialization. So if you need to debug the initialization code, you can. It's just not as easy as it would be after you get the thing to actually load. But honestly, if you're having a problem getting your module to initialize at all, then you probably have more problems than you know what to do with at this point. The reality is to initialize the module is very simple. Just return 0, and you've gotten past the initialization code. So it's not necessarily one that we have to do this very often, but it can be. Now, once I have the breakpoint initialized and I hit the breakpoint, then what I can do is in my debugger, I can do an add symbol file to it. I'll add my driver.ko and the address of where the symbol file is supposed to be loaded. And then I'll usually set that up to the entry point of .init.txt. So this will then allow me to come into the debugger. I will then have the symbol file from my driver into the debugger, and now I can set breakpoints and start working from there. I have 3 places that I normally set breakpoints anytime I'm trying to do kernel debugging. The first is I'm going to set a breakpoint at oops, I'm going to set a breakpoint at panic, and I'm going to set a breakpoint at sys_sync. The advantage of setting it, of course, the oops and the panic are pretty obvious. If you're encountering an oops or a panic, you're going to trap to that point, you'll jump out to the debugger. But sys_sync is not necessarily as obvious. The reason that you put a symbol, that you put a breakpoint at sysync is so that from the user's command line, you can type the command sync from the command line and it'll trap to the debugger. That gives you an easy way of being able to always jump into the debugger from user space. So as long as you have those breakpoints set, you should be good as a good starting point, and then you can start stepping through the code from there. Now, if your module init is working, then you don't really need to worry about having to debug the early initialization code. So what you're going to do is you're going to look in sys modules, module name, sections. There's a file in there called .text, and it's a hidden file. So if I were to look here at my entry point here. So here I have a module that I've got loaded, and I have, if we just did an ls in this directory, it looks like there's nothing here. But if you know that there's actually all these things begin with a dot, you realize that it's really a whole bunch of entry points. So the one that I'm interested in is the .text. So if I do an ls, or excuse me, a more here on .text, especially if I can spell more. I was doing less, but I'm sorry, it's not loaded at the moment. Let's see here, I've got data segment, text segment, init.text. I have a very simple application out here. It's really not much to speak about. Let's take a look here at the init.text. And it's showing up as a 02. Oh, I know why. Duh. Sudo more.text. There we go. Has to be root in order to be able to get this information. But I'm running a 64-bit kernel at the moment, so we see where it's located up in 64-bit space. So that's how, once we have that address, that's the address we tell the debugger to find the symbols at. And now we can set breakpoints inside of the debugger interface. So JTAG, single wire, serial wire debug, adds a pretty significant capability when you were debugging not only microcontrollers, but also the Cortex-A series parts. However, they do require access to the JTAG pins, and they also require that the JTAG pins haven't been fused out. Unfortunately, a lot of manufacturers, especially companies like Samsung with their Exynos parts, will blow the fuses, they'll blow the E fuses that give you access to the JTAG interface. They're afraid you're going to get into their part somehow and reverse engineer something significant. So they'll blow the E fuses and you won't be able to access the JTAG interface. But assuming that your manufacturer is actually friendly enough to allow you to have access to the JTAG interface, then you should be able to use this interface as a way of being able to not only debug source code, but also debug the early boot cycle that's typically done in assembly language. You actually get quite a bit for a $75 JTAG. You can get all kinds of information out of something like that, but if you want to have the trace macro support, if you want to have all the rest of that fun stuff that really gets into the low-level details of having debugged the physical hardware, then you really need to start thinking about spending a lot more money for a JTAG. Again, typically 5K, 7K, somewhere in that general range will get you just about everything you would ever need to have in a JTAG and a trace module. And it'll give you, a few megabytes worth of trace back, so that's actually pretty decent. Despite the low cost, OpenOCD, of course, is free. The Wiggler style interfaces are about 75 bucks, depending on whose manufacturer you happen to be picking. So they actually make a pretty decent combination for ARM debugging. Unfortunately, I don't have enough time to actually go through a process of a debug for you, but at least you get the general idea of what the process is, so hopefully you'll be able to go from there. Obviously, in my email here is right there. So if you want to reach out and contact me, I'll be happy to kind of lead you through the process. I have some much more detailed versions of this presentation that go into the details of how you actually set up all the addresses and everything. So if you're interested, send me an email. I'll be happy to send that to you as well. So any questions? Yes?
I didn't see anything with regards to the optimizations.
Okay, so the question is, I didn't see anything with regards to optimization. Optimization, when you turn that on in the kernel, and you almost always have to do that to inline stuff in the kernel, it simply means that when you're looking at that in the output for in the debugger, you'll actually see the debugger instruction pointer go backwards. It's a weirdness, you just have to accept it. You also have to watch out because some variables may have been optimized out. So you may be looking for variable values that aren't being used, and therefore the compiler said, well, he's not using it, I'm going to go ahead and I'm going to optimize it out, so sorry, sucks to be you. That is unfortunately the nature of what we're dealing with when we're dealing with the kernel. So, I mean, yes, I run into that all the time, and when I see the instruction pointer go backwards, it's like, okay, optimizer kicked in. Normally you're not going to be able to link it in without having the optimizers turned on. So you just kind of suck it up. You can't lower the optimization level much below optimization level 2 because you need to be able to inline functions. You can then specify an additional command line option to inline the functions. So yeah, you can turn it down a little bit further than that, but the reality is that it's going to change the timing of everything in the kernel, and therefore you may not necessarily be able to see the same error that you're seeing when the kernel has optimization turned on. Other questions? Yes?
You mentioned a couple vendors of JTAG UIs and stuff, but you mentioned DS5. Do you have any experience with it?
The ARM debugger, there's two different versions of that. So the question is, what about DS5? It's one of the ARM, it's the ARM community debug. Well, they have two different versions. They have the ARM community version, which is all open source, and then they have the official ARM version, which you pay money for. It's a decent debugger interface. It understands core site very well. It understands being able to take advantage of the trace macro cells. So in terms of if you have the money for it, it's a great debugger. They will normally, ARM doesn't actually sell the debugger interface piece, the physical interface piece. You'll buy somebody else's physical interface, but they'll use Lauterbach or they'll use one of the normal upscale versions of the debuggers. You won't be able to use the $75 JTAG to do that, but if you have one of the more expensive ones, then yes, it'll typically interface to DS5. So it's a fine interface. I just don't use it myself because the community version is hobbled, and if I'm going to be hobbled, I might as well do it with complete open source.
You talk much about multi-core debug.
With which?
Multi-core.
Oh, multi-core debug. Honestly, with multi-core debug, most of the JTAGs, most of the expensive JTAGs, have support for multi-core. So you can actually set breakpoints in individual cores. You can also stop the entire SoC so that you can then see the interactions between the cores. OpenOCD has recently added multi-core support, but it's not terribly mature based on what I've seen so far. I mean, I could be wrong on that, but I haven't seen it really do what I would like for it to do. And as a consequence, if you've got a commercial debugger, if you've got a commercial JTAG, you're probably better off with multi-core. But yes, you can do multi-core debug.
It depends on probe, right?
Depends on the probe. Okay, thank you very much. I appreciate it.